A modern smartphone processor under a heavy graphics load generates a massive amount of heat. Within seconds, the chip begins vibrating and radiating thermal energy until it simply shuts down to protect itself. When heat gets trapped inside a phone, two things happen. First, the device aggressively slows down its own performance to stop the temperature from rising further. Second, the trapped heat slowly bakes the lithium-ion battery, permanently degrading its internal chemistry and reducing its lifespan. This diagram shows exactly why cooling a phone is so difficult. A desktop computer cools its processor using a massive metal tower of fins stretching upward. But a phone is bound by the z-axis. The z-axis is the mathematical dimension representing the physical depth or thickness of an object. A phone is a flat glass sandwich, barely 8 millimeters thick, leaving zero room for vertical airflow. Because heat cannot travel up, engineers have to force it sideways. The thermal energy has to be spread outward along the flat XY plane of the phone's body, absorbing into the metal frame before it can cook the processor. The limit on how fast your phone can run is no longer determined by how many transistors fit on a piece of silicon. It is dictated entirely by how quickly we can move that heat out of the device. To get around this strict spatial constraint, engineers rely on a passive liquid cooling system called a vapor chamber. This diagram reveals the inside of a vapor chamber. It is a flat, vacuum-sealed copper envelope containing a tiny amount of liquid coolant resting directly above the processor, with empty space above it. Because the chamber is a vacuum, the internal pressure is incredibly low. This allows the liquid to boil and flash into vapor the instant it touches the heat from the chip, rapidly rushing outward through the empty space. As that hot gas spreads to the cooler outer edges of the phone's frame, it drops its thermal energy. The gas cools down and condenses back into discrete liquid droplets. Those droplets then return to the center through capillary action. Capillary action is the ability of a liquid to flow through narrow spaces without the assistance of external forces, like gravity. The chamber's internal copper walls are lined with a porous wick that acts like a sponge, physically pulling the liquid straight back to the heat source. This continuous passive cycle of liquid turning to gas and back to liquid absorbs and moves heat constantly. It allows paper-thin devices to run heavy calculations for hours without a single moving part. But some extreme applications, like sustained high frame rate 3D gaming, generate heat faster than a passive copper wick can return the liquid to the processor. When the passive system gets overwhelmed, manufacturers turn to active liquid cooling. This approach replaces the passive sponge with mechanical circulation. This diagram illustrates an active cooling loop powered by a piezoelectric micropump. A piezoelectric micropump is a tiny mechanical device that uses electrically stimulated crystals to physically push fluid through a system. This pump forcefully accelerates the liquid coolant away from the hot processor. To make sure the boiling hot liquid doesn't flow backward, the channels are lined with one-way check valves. As the fluid is pumped forward, these mechanical gates snap shut behind it, creating a high-speed, one-way racetrack. The rushing fluid arrives at a radiator zone near the edge of the device. Here, a high-speed microfan kicks on, physically expelling the gathered thermal energy through an exhaust duct and out into the open air. When the natural physics of evaporation and condensation hit their limit, engineers have to build complete microscopic mechanical engines just to keep the silicon stable. Instead of violently overheating, the processor remains perfectly stable, supported by this continuous, abstract flow of cool liquid, pulsing with rhythmic momentum. Keeping temperatures down is a hard requirement for the next wave of mobile tasks, specifically on-device AI processing. On-device AI processing means executing complex machine learning algorithms directly on your local hardware, rather than sending data away to a remote cloud server. Advanced computational photography tasks, like rendering 4K video in real time, or using AI to remove visual noise from a burst of photos, require the processor to run at maximum capacity. Without an aggressive liquid cooling loop, these operations cause the device to throttle and crash. Unthrottled performance is also the limiting factor for extended reality, or XR. XR is an umbrella term covering technologies that overlay digital graphics onto the physical world. If a phone overheats while rendering these graphics, the frame rate drops, and the user instantly loses the illusion of immersion. The modern smartphone manages all of this by housing millions of microscopic rapid weather systems, constantly raining and evaporating beneath the glass. The software innovations we expect to use tomorrow are dictated entirely by our ability to control these invisible thermodynamic storms today.